Welcome to the fifth lecture of this week. So, we will continue our discussion on higher order shear deformation theory. In the previous lecture, we saw that in the higher order shear deformation theory that we are considering, the kinematic assumption has terms up to z cube, and then we and it had few number of unknowns in the model, and then by satisfying the condition that our transverse shear strains are 0 at the top and bottom, we are able to reduce the number of unknowns. And in fact, we have seen the number of unknown here is equal to the number of unknowns we had in the previous first order shear deformation model, but the relationship is nonlinear here, nonlinear in Z, and then based on that we derive the strain displacement relationships. Now, we will today start with the stress strain relationship, and from there we will find out the laminate constants, and then we will see the governing differential equations. So, stress strain relationship the stress strain relationship, if we consider the in plane stress components sigma x, sigma y, sigma s, we know that they are related through this matrix that does not change. Same matrix that we derived before, and this gets multiplied with epsilon x, epsilon y, epsilon s, and those are, as we discussed in the last class, this vector plus a vector which gets multiplied with z plus a vector which gets multiplied with z cube. And this is in the x y direction. Similarly, for transverse terms we have tau x z and tau y z. The stiffness matrix remains same. We derived it in the third and fourth class, in the third class specifically. So, we have q x z, q x x z, q x y z, q x y z, and q y y z, and then this gets multiplied with the transverse shear strain which we denote as gamma x z 0, gamma y z 0, and this gets, and then another vector which gets multiplied with z square. So, that is kappa x z 2, kappa y z 2. Again these twos are not squares, rather they are superscripts. Now, from here we find out the stress resultants, and that will give us the laminate stiffness terms. So, stress resultants, the first set of stress resultant that we derive are the in plane forces. So, we have Nx, Ny, Ns, we already know what these terms mean, and that is integral of sigma x, sigma y, sigma s along z. Now, because these quantities are ply dependent, so we have to integrate over each ply and sum up. So, this goes from zk minus 1 to zk, and then we have the q matrix in the xy system for the kth laminate, and then we multiply that with this same vector x epsilon x y, epsilon x, epsilon y, epsilon s 0 plus z into kappa x 0, kappa y 0, kappa s 0, plus we have z cube into kappa x 2, kappa y 2, and kappa s 2. Now, if I look at this term multiplied by this, this we know it does not, it is not a function of z. So, only q is a function of z. So, if I integrate that and sum it up, that gives us an A matrix which we are already familiar with. So, it becomes A matrix multiplied by this, and then we have q multiplied by z, and q multiplied by z on being integrated and summed up gives us a matrix called B, and B is kappa x, B gets multiplied with kappa x 0, kappa y 0 and kappa s 0, and then we have z cube into q integrated and summed up, and that gives us a new matrix which we can call as E. So, E multiplied by kappa x 2, kappa y 2 and kappa s 2. So, here we define E as summation k equal to 1 to n z k minus 1 z k integral of z cube into q dz. Now, let us find out the moments, the resultant moments, and those moments mx moment with respect to y axis, my moment with respect to x axis, and ms the twisting moment, that is summation k from 1 to n z k minus 1 z k, and then we multiply z with sigma x, sigma y, sigma s, and then integrate, and that is k is equal to 1 to n integral of z multiplied by q matrix for the kth lamina in the xy system, and this is multiplied with the same set of vectors epsilon x 0, epsilon y 0, epsilon s 0, plus we have z into kappa x 0, kappa y 0 and kappa s 0, sorry kappa x 0, kappa y 0 and kappa s 0, plus we have z cube multiplied by kappa x 2, kappa y 2 and kappa s 2. Now, this can be written as a B matrix multiplied by epsilon x 0, epsilon y 0, epsilon s 0 plus D matrix multiplied by kappa x 0, kappa y 0, kappa s 0, plus we have another matrix which is z into z cube, like z to the power 4. So, z to the power 4 into q integrated and summed up, and that we call as F matrix. So, F matrix multiplied by kappa s 2, kappa y 2 and kappa s 2, where we define F matrix as k is equal to 1 to n z k minus 1 z k z to the power 4 q matrix with respect to xy system for the kth ply integrated and summed up. Now, we have to define the resultant shears in the transverse direction, and those are Vx and Vy, and for that again we just have to sum up the integrals. So, we have here the q matrix in the xy system corresponding to the transverse direction, which we have defined before while discussing the first order shear deformation, the same Q matrix is here, but we multiply with two vectors. So, one is gamma xz0, gamma yz0, and plus we have z square multiplied by kappa s2, kappa y2, and this gives us a matrix A with a superscript z, because this A matrix is not same as the A matrix we used for the nx, ny, ns. So, this is for transverse components. So, we have a superscript z, we already saw this, and this we multiply with the vector gamma xz0, gamma yz0, and plus we have a new vector z square multiplied by this Q matrix, I mean qz, integrated and summed up, and this we call D matrix, and D matrix is kappa x2, D matrix gets multiplied with kappa s2 and kappa y2, the vector of that. So, we have a new matrix called D with a superscript z, and that D matrix is equal to summation 1 to n, k equal to 1 to n, integral from zk minus z, from zk minus 1 to zk of the Q matrix with respect to x y for the kth layer, and this is qz. So, this multiplied by z square, integrated and summed up. So, with this the definition of the laminate stiffness are completed. So, with using this laminate stiffness quantities, we can relate the stress resultants nx, ny, ns, mx, my, ms, and vx and vy, that means out of plane shears, So, those we can relate them with the displacement components, I mean the derivatives of the displacement components. Now, let us look at the governing differential equations. So, the governing differential equation, as we know, it is del nx by del x plus del ns by del y minus we have integral from zk minus 1 to zk of rho into u double dot, and then we sum up the integral, and that is equal to 0. So, this is the inner shear term. Now, in U we have to put the definition as per our kinematic considerations, and then that would give us the equation in terms of those components which have in the kinematic consideration, and finally that becomes I0 into U0 double dot minus I1 minus 4 by 3h square of 3h square into I3 multiplied by psi x double dot, and then we have plus 4 by 3h square I3 into del w double dot by del x. So, here we get a new quantity called I3. So, where I3 is defined as integral of rho z cube from zk minus 1 to zk, and then sum up over all the applies. Similarly, the second governing the differential equation becomes del n s by del x plus del n y by del y minus I 0 into V 0 double dot minus I 1 minus 4 by 3 h square into I 3 psi y double dot plus 4 by 3 h square into I 3 into del w double dot by del y equal to 0. And the third governing differential equation is del V x by del x plus del V y by del y plus q multiplied by I 0 w double dot. The fourth one is del m x by del x plus del m y by del y minus V x. So, here q is the applied load in the previous equation, we already know what these quantities mean, and then we have minus I 2 minus 4 by 3 h square I 4 psi x double dot plus 4 by 3 h square I 4 del w by del x equal to 0. So, we have seen before that when we write this differential equation in the inertia term, we have a term like k equal to 1 to n z k minus 1 to z k into integral of rho z u double dot dz, and that is what gives us all these terms. Similarly, the last equation is del m s by del x plus, okay, in the previous equation there is a correction, it is del s plus del m y by del y minus V s minus I 2 minus 4 y 3 h square I 4 sigma y double dot plus 4 by 3 h square I 4 into del w double dot by del y equal to 0. So, these are the 5 governing differential equations, and again the rest of the procedure is same. We can directly solve the governing differential equation. For that if we want to do a Navier solution, our lamination sequence and the boundary condition has to permit that. In that case, we do separation of variable and write the x and y dependence of the solution variables as double trigonometric series, and then we put it in these equations, and then we separate out the trigonometric terms and rest of the algebraic terms are set equal to 0, and that give us the solution. We can do Navy type solution if we can, and otherwise energy or virtual work based solution is always possible. So, for that we write, instead of writing this differential equation, we write the corresponding energy or virtual work equation and then put our assumptions there, and then we say that the coefficient to each of the variation term is 0, and by setting them to 0 we get a set of algebraic equation for static problem or eigenvalue problem for buckling or the free vibration problems, and then by solving those we can get our desired quantities. Now, these were just 2 shear deformation theories, but there are many of them. There has been several advancements in this field. In case of composites, the relevance of this shear deformation theory is more, or the importance is more, because composites suffer from something called interlaminar stresses. So, if I look at a composite ply, a composite laminate made of few layers, and we know that even if we have a pure extension, the strain is continuous, but because the strain is continuous and the material properties with respect to xy system of different plies are different. So, that makes us, that gives discontinuity in the stresses. So, we can have something like this depending on the type of the laminate. Say if it is symmetric laminate, we can get this kind of stress profile. So, there are stress jumps, and it can happen due to it can happen in case of bending also, or any other case. Strain remains continuous for compatibility, but stress becomes discontinuous. So, at the junction, the two plies under two different normal stress tries to separate or slip over another. So, to hold them together, an enormous amount of shear stress generates here, and that is needed to hold the plies together. So, if I look at an element, say this is our x z plane, same phenomena can be seen in y z plane also. In that case, we see the generation of interlaminar shear stresses. Now, we know that the shears are complementary. So, these shears will also generate. So, these are the transverse shears tau x z and tau y z. So, proper calculation of this tau x and tau y z are required, and also we need to calculate them without adding too much of computational complexity. So, with that motivation, there has been so many theories developed. So, these were two theories, there are many other theories. So, interested learners can look into different papers and learn about these theories. So, this brings us to the end of the discussion on shear deformation. Thank you.